Hello and welcome to Georgia. I'm Tim Strickland, Research Leader of the Southeast Watershed Research Lab, where we have a 52-year legacy of research in the Little River Experimental Watershed. SEWRL is home to the Gulf Atlantic Coastal Plain LTAR site and is one of the original 14-seat benchmark watersheds. The unit scientist employs systems approaches in combination with dense real-time monitoring networks and state-of-the-art labs to meld NP211 objectives with those of NP216, Sustainable Ag Systems, and now 304, Crop Protection and Quarantine, in order to provide stakeholders with information to balance ecosystem services and profitability in complex landscapes. Future research will focus on incorporating edge computing and artificial intelligence to enhance the conservation of soil and water resources while maintaining agricultural productivity and profitability. More information is available on the website indicated in this slide. Thank you for joining us.
Hello, I'm Dr. David Bosch, research hydrologist at the Southeast Watershed Research Lab and lead scientist for our NP211 project. The observations presented here are the results of a long-term study of the impacts of conservation tillage in coastal plain soils. We quantified crop yield, surface and subsurface flow, sediment, nutrient, and element transport, comparing conventional and strip tillage for cotton and peanut production. Some of the key findings and impacts were: there were no yield differences for the cotton or peanut crops studied. Our results indicate conversion to strip tillage reduces surface runoff by 50%, sediment losses by 85%, pesticide losses by 50%, and nutrient losses by 50%. Increased available water under strip till results in increased subsurface water loss by 70%. Net water impact is that there is no difference in total water loss. Nitrogen losses were dominated by strip till subsurface water loss. Winter cover crops reduce sediment loss and increase soil carbon and nitrogen. Strip tillage resulted in an enrichment of total organic nitrogen and carbon in the surface runoff, both by 50%. Conservation tillage is used on 70% of the cotton acreage in the southeastern U.S., and these results indicated as having a significant impact on water, sediment, and nutrient transport throughout the region. For additional information, please refer to our website shown at the bottom of the slide. Thank you very much.
In Florence, our research is focused on improving the region's water and nutrient use efficiency using variable rate irrigation systems in connection with decision support systems. The southeastern coastal plains includes highly weathered soils with sandy textures, low organic matter contents, and highly variable water holding capacities. The region's crop yields are impacted not only by fertilizer management, but by the large variability of rainfall during the crop growing season. This often requires supplemental irrigation. To address these issues, we developed a set of rainfall probability tables to inform growers on the potential for rainfall extremes in the regions. These tables should be useful in both irrigated and dryland agriculture. To better manage variable rate irrigation systems, we investigated using decision support systems. We used adapted the Irrigator Pro for corn for variable rate irrigation and found it to be effective in managing spatial irrigation, while it also improved nutrient use efficiency. As part of an ARS multi-location research project, we used an ARS developed variable rate decision support system called ARS Pivot that uses both crop canopy temperatures to detect plant stress and soil water measurements. It operates by first running a dry scan to measure the crop temperatures. It then calculates an integrated crop water stress index. From this, it develops a prescription map that is downloaded to the Center Pivot control panel. This novel system produced higher corn yields and improved water efficiency than a scheduling method using only soil water potential measurements. In a separate study, we measured the crop canopy reflectance using NDVI to estimate irrigation crop coefficients to develop prescription maps for variable rate irrigation systems for both corn and cotton.
Satellite remote sensing provides an abundance of near real-time data, which can feed our models and decision support systems. ARS has been critical to the development and implementation and validation of soil moisture products, such as those from the Soil Moisture Active Passive mission. 7 ARS experimental watersheds have been collaborating with soil moisture missions to assist in the calibration and validation of their products, allowing NASA and ESA to produce validated 9-kilometer global soil moisture products that would not be possible without ARS. These watersheds continue to participate and provide the premier CAVAL network for soil moisture remote sensing, as well as for data products from models.
The GRAPE Remote Sensing Atmospheric Profile and Evapotranspiration Experiment, GRAPE-X, began in 2013 and is aimed at developing a multi-scale remote sensing vineyard water management toolkit. It is the result of a private-public collaboration between NASA, USDA ARS, Utah State University, and Gallo. The recent publication of the GRAPE-X project in the Bulletin of the American Meteorological Society, or BAMS, describes preliminary research results from this multidisciplinary project. ARS Hydrology and Remote Sensing Lab team used an array of remote sensing capabilities with their ET toolkit for mapping vineyard water use and water stress to improve irrigation scheduling and management. Output from this modeling system from regional to field scales is illustrated in the center figure. The figure on the right top illustrates the capability of the ET toolkit to define areas of vine stress and over-irrigation in this vineyard block containing a variable rate drip irrigation system, or VRDI. The VRDI can prescribe irrigation amounts over a 30 by 30 meter grid, matching the mapping resolution of the ET toolkit, and as the bottom illustrates, achieve uniform grape conditions. Gallo currently can achieve 10 to 15% water savings in most vineyard blocks, but in some cases they foresee saving up to 25% in applied water. It is envisioned that this ET toolkit can be expanded to the nearly 950,000 acres in California producing raisin, wine, and table grapes. In addition, plans are to expand the ET toolkit to nut and fruit orchards, where California almond orchards alone occupy over 1.5 million acres.
The cranberry industry has identified adverse impacts on water quality as one of the greatest threats to continued production in the densely populated near-coastal areas of eastern Massachusetts. Water stored in holding ponds originates from runoff and drainage of upland agricultural soils and is already enriched in peat before being used to irrigate and flood cranberry bogs. ARS scientists, in collaboration with NRCS, the University of Massachusetts, and local cranberry growers near the Cranberry Research Station in East Wareham, tried managing surface water inputs by treating the holding ponds with aluminum sulfate to flocculate organic NP and absorb dissolved P. Sandbarge was used to distribute the aluminum sulfate across the pond surface. The researchers found that treating the water prior to it being used in cranberry production reduced total P losses and bog drainage by 20% and nitrogen losses by a lesser amount. Producers say cleaner water in holding ponds also reduces clogging of pumps and irrigation systems. ARS scientists are currently working with NRCS staff to develop an interim conservation practice standard and promote wider on-farm trials to document the effectiveness of the practice across different landscapes, environmental conditions, and management systems.
The Common Experiment for the Upper Chesapeake Bay Long-Term Agroecosystem Research Network site at University Park, Pennsylvania, compares a business-as-usual dairy forage cropping system to an aspirational system. Large plots, 1/20th of the size of the field that they represent, are managed to meet the goals of both systems. Crop yields and forage quality produced in the plots are used as input for feeding virtual dairy herds on each farm to model milk production and profits. Manure injection, an aspirational management practice, has multiple advantages, both economic and environmental, over traditional surface spreading of liquid manure. One of the greatest advantages is the conservation of nitrogen that would otherwise be lost by ammonia emission. That nitrogen remains available for crop use and negates the need to side dress with purchased commercial fertilizers to meet crop needs. Phosphorus losses in runoff is also minimized.